Hello, I'm Shingo Uchida from University of Tsukuba, Japan. In this presentation, I'm going to talk about adaptive link rate switching based on traffic splitting method for power saving. In recent years, many network devices such as smartphones and tablet PCs are widely spread. As a result, internet traffic is rapidly increasing and the power consumption also increases. To reduce their power consumption, many researchers are studying power saving of the wired network. One of the software approaches for the power saving is adaptive link rate. ALR switches the link speed according to the link utilization. Based on ALR, we previously proposed the link rate switching method on OpenFlow networks. However, this method only supports multipath TCP. In order to provide the previous method for other protocols, this presentation introduces the traffic splitting method to our previous method and proposes a new AAR switching method to support other protocols such as TCP and UDP. In Ethernet, the power consumption is not much affected by the link utilization, but is dominated by the link speed. So ALR switches the link speed according to the link utilization. In ALR, all link rate set to the low rate at first. In this slide, there are two paths between the host and the server. All link are gigabit Ethernet, and the low rate is 100 megabits per second. When the traffic at this link exceeds 100 megabits per second, ALR switches its link speed to the high rate, 1 gigabits per second. But the added 900 megabits per second may be too many. The power consumption may not be appropriate for the link utilization at this time. To solve this problem, our previous method introduces the middle rate. As shown in the slide, the middle rate is constructed from multiple low-rate links. In this slide, these two links provide 200 megabits per second for the middle rate. So when the traffic exceeds 100 megabits per second at some low-rate link, our previous method doesn't switch to the high-rate link immediately, but uses the middle rate. Since the middle rate links consume less power than the single high-rate link, the power consumption is reduced from that of simple ALR. However, our previous method supports only MPTCP to split subflows of the traffic into multipaths at the middle rate. To support other protocols such as TCP and UDP, we propose a new ALR switching method. This method works on OpenFlow networks and uses the traffic splitting method, which is based on OpenFlow metatables. The proposed method also uses metatables for other operations. Next, we will introduce OpenFlow networks. In this OpenFlow network, the OpenFlow controller controls these OpenFlow switches. Basically, each OpenFlow switch operates according to the flow table. The flow table is configured by the OpenFlow controller and consists of multiple flow entries. Then, flow entry has mainly these 5 fields: match field, instruction, priority, cookie, and timeout. When a switch receives a packet, it compares the packet to the match field. And then, the instruction is executed when the packet matches the flow entry. In this switch, a packet from the port 1 matches this flow entry and sent to the port 2. If a packet matches more than one flow entry, the flow entry with the highest priority is applied, and the packet is processed according to the instruction field. The OpenFlow controller can store a cookie in flow entry to identify the flow entry. If a flow entry has timeout field and the timer has expired, then the flow entry is deleted from the flow table. At this time, the OpenFlow switch can send a flow removed message to the OpenFlow controller. In the instruction field of the flow entry, various operations can be configured. The apply action is used to output packets or send to multiple ports using group action. GoToTable is used to jump to another table to allow pipeline processing. The most important instruction for the proposed method is meta. The meta instruction performs an action based on the traffic rate. As shown in this meta table, meta is identified by meta ID. Each meta has a band type and rate. When the traffic exceeds the rate, an operation is processed on the packets exceeding the rate according to the band type. If the band type is dropped as in this entry, the packets exceeding 100 megabits per second are discarded. If the band type is DHCP remark as in this entry, the differentiated services code point field in the IP header of the excess packets are set to the value 10 in the type-specific argument. The traffic splitting method uses this DHCP remark to classify packets by the value in the DHCP field. The proposed method also uses the DHCP remark meta to perform other operations such as traffic aggregation. We'll explain the proposed method from the example network topology in here. These switch 1, switch 2, and switch 3 are OpenFlow switches. H1 and H2 are hosts. The number in these indicate port numbers for general communications. In the proposed method, all these link rates are set to the low rate. Note that the low rate will be 100 megabits per second, and the high rate will be 1 gigabit per second in the evaluation. All the switches are also connected to the OpenFlow controller via the extra port. The proposed method assumes that the controller can change each link rate between switches. For example, the controller may send a command over SSH from these extra ports. Now, when H1 sends the traffic to H2, there are two paths. One is the shortest path, and the other one is bypass through switch 3. In this example, H1 sets the DHCP value of all its packets to 10 to send these packets over the shortest path. This diagram shows the control for the traffic at switch 1 with the meta tables. When a traffic with a DHCP value of 10 arrives at switch 1, meta 1 measures the traffic at first. If the traffic does not exceed alpha megabits per second, it is forwarded to switch 2 over the shortest path. Otherwise, the part of the traffic up to alpha megabits per second is forwarded over the shortest path, but the rest part over alpha megabits per second, switch 1 changes the DHCP value to 12 to send it via the bypass. But meta 2 also measures for the rest traffic to check whether the rest traffic exceeds the capacity of the bypass or not. If it does not exceed beta megabits per second, both the shortest path and the bypass are used to provide the middle rate. Otherwise, switch 1 notifies the controller to switch the link rate of the shortest path to the high rate and aggregate these two paths to the shortest path. Note that since there is some delay to change flow tables, alpha should be smaller than the low rate. For switching to the high rate, since some packets are sent via the bypass before the shortest path is set to the high rate, so beta should be smaller than alpha. For example, in the evaluation, alpha and beta will be set to 90 megabits per second and 80 megabits per second, respectively. From here, I'll explain how the controller operates the flow tables, meta table, and group table in switch 1 in the proposed method. Initially, the controller sets them up like this and set all the link rates to the low rate. When H1 sends a packet to H2 via port 1 of switch 1, the packet matches to this entry in this flow table 0. Then, meta 1 is applied according to the instruction. In case 1, the traffic does not exceed alpha megabits per second, and then the DHCP value remains to 10. Next, go to table 1 is applied and continuous processing with this flow table 1. From this entry, the packet is output to port 2 to pass through the shortest path. In case 2, the traffic exceeds alpha megabits per second, and then meta 1 sets the TCP value in the packet to 12. Then, from this entry, the packets exceeding alpha megabits per second are measured at meta 2. But meta 2 does nothing because the excess packets don't exceed beta megabits per second in case 2. So, from this entry in flow table 2, the excess packets are output to port 3 to pass the bypass. Note that the traffic splitting method proposed these case 1 and case 2 to increase throughput. For power saving, the proposed method introduces the following cases to realize ALR. In case 3, the excess packets exceed alpha plus beta megabits per second. So, meta 2 changes the DSCP value in the excess packet to 14. Then, from this entry, the group action is applied. Group action can handle multiple actions at the same time. From this group table, group 1 outputs the excess packet to port 3 and send the packeting message to the controller in the same time. If the group table is not used, the excess packet must be output after the packeting message is sent, but this process takes for a long time. When the controller receives the packeting message, it executes algorithm 1 to aggregate both paths and switches the shortest path to the high rate. These new flow entries with high priority are added by algorithm 1. Next, I'll explain how to use the new flow entries. When H1 sends a packet via port 1, the flow table 0 is applied, and then the new flow entry is matched since its priority is high. So, the meta 3 measures the traffic. When the traffic exceeds the middle rate, alpha plus beta megabits per second, the exceeded traffic is matched to this new flow entry, and then output to port 2. Note that this flow entry sets a cookie and timeout counter. When the flow entry is matched, the timeout counter is reset to the initial value time x. The rest part of the traffic below the middle rate is also output to port 2 from this entry. In case 5, the traffic becomes lower than alpha plus beta megabits per second after the traffic aggregation. In this case, although meta 3 measures traffic, its DSCP value stays at 10. So the packets are output to port 2. So this new entry is no longer matched and its timeout counter is expired. Then the switch deletes this flow entry and notifies the controller by sending a flow removed message with the cookie. From the flow removed message, the controller executes this algorithm 2 send flow modify message to delete this flow entry. As a result, switch 1 returns to case 2 at the middle rate. From here, I will explain about communication experiments to confirm the feasibility of the proposed method. This table shows the experiment environment. The experiments used the OpenFlow controller Liu on the network emulator Mininet. The OpenFlow version is 1.3, which supports metatables. In this topology, a UDP traffic stream is transmitted from H1 to H2 by iPerf. This figure shows the throughput in the shortest path and the bypass and the total throughput at H2. In this experiment, alpha is 90 megabits per second, beta is 80 megabits per second, and time x is 10 seconds. At first, H1 sends 50 megabits per second UDP traffic flow to H2 for 10 seconds. This figure shows that the traffic only goes through the shortest path for this interval. After 10 seconds, H1 sent an additional 100 megabits per second UDP traffic flow for 40 seconds to H2. At this time, the traffic splitting begins. About 90 megabits per second throughput is observed in the shortest path, and 60 megabits per second is observed in the bypass. This shows that the proposed method provided the traffic splitting at the middle rate. At 20 seconds, ASON sent the second additional 100 megabits per second traffic flow for 10 seconds. From the figure, about 250 megabits per second throughput is observed in the shortest path, and no throughput exists in the bypass. So the proposed method provided the traffic aggregation. At 30 seconds, the second additional traffic flow stopped, but the proposed method maintained the traffic aggregation for 10 seconds since the time x is 10 after the final packet of the second additional traffic has been matched to the flow entry. At 40 seconds, the flow entry for traffic aggregation was timed out, and then the proposed method split the traffic again. In this figure, the total throughput from 30 to 40 seconds and from 40 to 50 seconds are almost equal, so the splitting traffic did not lose any throughput. Finally, when the first additional traffic flow stopped at 50 seconds, the split traffic flow were aggregated on the shortest path with a low rate, and no traffic exists in the bypass. Next, to evaluate the power consumption, the power consumptions of the proposed method, non-ALR and simple ALR are calculated. In non-ALR, all links are always set at a high rate. In simple ALR, all links are normally set at a low rate, but the rate of the shortest path is changed to the high rate when the total traffic rate exceeds the low rate. In both cases, no traffic is split. Based on the reference 21 in our paper, we calculated the total power consumed by the switch by this equation. From the reference 21, we also set these variables like these. The figure shows the total power consumed by all switches. Compared with non-AR, the proposed method reduced 2.1 watt at the low rate and middle rate, and 1.4 watt at the high rate. Compared with the simple AR, the power consumption of the proposed method is almost the same at the low rate and high rate, but reduced 0.7 watt at the middle rate. This is because the proposed method can use the middle rate. At the middle rate, the shortest path and the bypass are at the low rate. The total power consumption of both paths is lower than that of the shortest path at the high rate. But this result shows just instantaneous power consumption. We should evaluate total power consumption for a more long time. This figure shows the daily traffic pattern from H1 to H2 as considered for a campus network in our previous method. The table shows the total power consumption by this traffic pattern. From the table, the proposed method is calculated that it will reduce 10.35 watt-hour compared with simple AR, and 47.6 watt-hours compared with non-AR. In this presentation, we proposed an adaptive link rate switching method for power saving based on the traffic splitting method using OpenFlow metatables. The proposed method can provide a middle rate for communications other than MPTCP. In addition, the contribution of the proposed method is to enable the control based on the current traffic without monitoring the traffic by an OpenFlow controller. In general, an OpenFlow controller needs to measure the traffic for such controls, but the proposed method only needs to be measured by metatables in each OpenFlow switch. So the load of the OpenFlow controller should be lower than that of our previous method. From the calculation, the power consumption may be reduced from those of the non-ALR and simple ALR methods. So the proposed method should be implemented into a real network to measure the performance and power consumption. When a link rate is switched, network communication may be subject to a slight loss of packets at the moment of switching. We will plan to implement a control to avoid link disconnection during the switching in the future. That's all. Thank you for listening.